And here we are, rendering, lighting and materials, making stuff beautiful. Now that you put in your data, you did your mesh editing, you did the basic stuff, we need to make it pretty. So what are the goals of this section of the course? To understand how light works in Blender, because it doesn't go the same way as it does in real life. Getting familiar with the camera settings, understanding the effect of different types of light sources, change the look of your image with materials, improving your render performance. So, as I said, we're at the end of the pipeline. We do some things in the scene still with the camera maybe, and render the image and make it look beautiful. But first, we need to know how it works in real life. In real life, when you have a light source, for example, in this image, the sun, it will shoot out rays in all directions, and it will hit objects and bounce off these objects and refract into the scene and all over the scene. And eventually these light rays will bounce enough until they reach the retina of your eye or a sensor of a camera. And that will then generate an image out of it. But actually, that is for a computer program very inefficient, especially when you have a lot of light sources. Then you have a lot of rays shooting around the scene that don't hit a retina or don't hit a sensor, and that is just wasted computation. So what we do in a computer program is the reverse. We shoot camera paths instead of light paths, actually. So for each pixel within the camera, for each pixel within the sensor, it will shoot out multiple rays, and these rays will bounce around into the scene, and at every bounce they will collect a little bit of light information until it terminates, and then it accumulates all this light information and stores it within the pixel value. So this is how it works in cycles. In cycles, as I said, it will shoot a ray out of the camera, and at every point it bounces, it will shoot a shadow ray toward a random light source it chooses. And if there's no object in between, it will accumulate light information from the bounce point, and it will bounce further, and then it's a reflection ray. And if you have a transmissive object, it will become a transmission ray, and afterwards it will become a transmission ray. It's way more complicated than that. It's a very intricate algorithm behind cycles, but this is the basics on how it works. So what we're going to do in this part of the course is basically manipulating these light rays throughout the scene with the starting position, the camera, second, the lighting, the light sources, where the light is collected from, and third, how the light rays bounce through the scene with the materials on the objects, and fourth, the rendering of the final image, so choosing the amount of rays shot through the scene, the amount of time it bounces, and when it terminates. So let's go to the start of the light rays, the camera. The camera has multiple settings, but the most predominant ones are the focal length. As you can see here, it basically zooms in the image like a real camera lens would do. And as you can see, the lower focal length values made a wide angle view, and the higher focal length values make a short angle view and a more zoomed in view. Second is depth of field. That is what you use to determine the focus of your image. That's what you want to use to put focus in a certain part of your image. And again, this works the same as in the real camera. You have a aperture and you have a focal point. The focal point determines the location on where the focus is, and the aperture determines the shallowness or wideness of the depth of field. This aperture is defined by a f-stop number. A low f-stop number has a very shallow depth of field, so the foreground and the background is fuzzy, and a high aperture value has a clear image throughout the whole scene. So that is it about the start, the rays, the camera. we're gonna now go to the light sources, which are the source of the light information. You have two major types of light sources within Blender. The global lighting, the world light as it's called in Blender, and the light objects, which are single light objects. The global light illuminates your scene from all directions, omnidirectional around your scene, with a certain color or a image, a 360 image, whatever you want. You can light your scene with it from all directions. And then the light objects, you have multiple light objects, which you can place multiple lights within your scene. You have point lights, sunlight, spotlights, and area lights, and they all have a different way of shooting their rays throughout the scene. So the point light, it collects rays from all directions, and the sunlight collects rays from one direction only, but throughout the whole scene, from one side which the sun is pointing from. And then you have the spotlight, which is the same as a normal lamp. It has a fanned out way of collecting lights, and you can determine the angle of the spot, and you can determine the center point, how the light is distributed within this arc. And then you have the area light, which is an area that emits light in the scene. And of course, for every light object you have different settings. You have color, which can change the color of the light. You have the power and strength of the light, and then you have the size or the angle of the light, and it depends on what kind of light source it is. For point, spot, and area, it's the size, and for the sun, it's the angle. And what this does, the size and angle, it determines the sharpness or softness of the shadow. As you can see here illustrated in this image, a low light size, the light comes from one single point, so the rays can only be bouncing from here to hit the light, but from here a little bit below it will not hit the light, so it's a very sharp shadow. And if you have a higher light size, it has a range in which between it can reach the light source, and that way you can create softer shadows. So you can also play with this within your scene. If you want to have more detail in your image and you want to see all the tiny detail, you need to have a low light source, and then you see sharp shadows, and then you can see a lot of detail. But for example, this is for the key light, it's important. Then you get a lot of details within your 3D model. But if you have a fill light, you want to fill it, and you will also want to fill the shadows with a little bit of light. So that way you use a bigger light source for a fill light. Now that we have the light information source of the scene, we're gonna go to the way stuff bounces off objects, and that is the materials. And Blender has multiple types of materials. The first one is pure specular, which is a perfectly smooth material, which doesn't exist in real life, so usually you don't use this one. But in this material type, the angle of reflection is exactly the same of the angle of incidence, and there's no randomness at all. And the glossy material, which is almost the same as the pure specular one, but the angle of reflection has a bit of randomness to it. So the angle of reflection is still positive, but it has plus and minus a little bit of reflection, and that reflection is determined by the roughness of the material. I don't know if it's visible on the recording, but you see there is slight roughness, and on this pure specular it's completely smooth. And the second one is the diffuse, where the reflection is pure random, determined by the roughness. It could also be a little bit glossy when you set the roughness completely low, but if you put the roughness completely up, the angle of reflection is completely random within this 180 degrees of the material. So it could be the positive or negative. And then you have transmission, the transmission material, which is for example, glass. It can also refract into the glass and refract out of the glass. But based on the index of refraction, which determines what angle of incidence will be reflected and what angle of incidence will refract into the glass and go out of it again. And the last material is the subsurface scatter, which is basically kind of like your skin. When you shine a light through your skin on the back, it looks red and you see some light going through. That is basically what subsurface scatter does. It will be the same on the surface as the diffuse, but sometimes light rays go inside the material and bounce around and shoot out again. And then you have the mother of all materials, which is basically the only material that I use because it has all the previous materials inside of one material. And this is the principled bidirectional scatter distribution function material. The principled BSDF, as it's called. It's a mouthful. But basically you can create almost everything within this one material. And this material is based on Disney's PBR shader, the physically based rendering shader within Hyperion, which is a rendering engine Disney uses for their Pixar movies. And within this material you have multiple settings which you can use to make all different types of combinations of materials. But inside it also has an algorithm to calculate a physically accurate Fresnel effect, which is the way the light bounces off the side of an object, which is with most materials is not included, but within this one it is included, so it makes everything look a little bit more realistic. Now that we know about the starting position of the light rays, the cameras, where they collect their light information from, the light sources, and the way they bounce throughout the scene on the objects, the materials, we're gonna go into Blender before we continue with the quality and performance, so that we see what kind of things you come across when you start rendering images. So I'm gonna open Blender now, and with this hands-on part you can just follow along with me, or you can just watch the video itself and just try it yourself later in the exercises. So when we open Blender we have this default Blender, and if we open a new file and we go to the rendering, lighting and materials walkthrough directory, and we'll go to the first section, the camera section, and then go to the camera blend file. And when we open this file we are greeted with three Suzannes looking through a camera. As you can see, the rectangle represents the viewport of the camera, and they are not all nicely in view. But what we now see is a solid shading, and for solid shading we don't really see what the light rays do within the scene. So when we want to look what the light rays are doing in the scene, we first need to activate the cycles renderer, and in this scene it is already activated, but if you want to change it anyways, you can change it in the render properties, in the properties panel, and go to the render engine and then select cycles. And if you then press now the Z key and go to render shading, you see one of the monkeys is in focus, and you have a nice rendered image with one of the monkeys on 1/3 of the image with a nice perspective. So if we now change our view position, just move your camera around, then we change the viewport position. It doesn't change the camera position, but only the viewport position, but as you can see, it looks super noisy. And that is because every time you change the viewport position or change the camera position, if you look through the camera, it needs to calculate the light rays again. It needs to shoot out the light rays from your view position and calculate for every single pixel a fixed number amount of times the value. And as you can see, it gets better and better when the amount of rays shot out of a pixel are increasing. So yeah, that's how this works with the starting position of the light rays. So if we go back into the camera, we can do that by pressing the 0 key on your numpad like this, or we can press view and then within view go to viewpoint and then to camera, and then you're also inside of the camera again. We're now going to go into the camera settings. The camera needs to be selected, so in our case it's already selected. And then if you go to your properties panel and you select the little camera, we're gonna make it a little bit wider so we can see what we're doing. Here you have all the camera settings within Blender. And as you might have noticed, with the changing of the camera position and changing of the viewport or changing the UI itself, it needs to calculate the light rays again. And that can take a lot of time. For example, if I change this, it needs to calculate everything again. And to reduce the stress on your system, you can also select an area in your viewport to render. So we do that by Ctrl B. And if you then select, for example, the first monkey, it will only shoot rays in this area and only calculate the light information within this area. And then it's not so taxing for your system anymore. And to remove this boundary again, you can use Ctrl-Alt-B, and then as you can see, it's slower again because it has to calculate the whole viewport again. But this is just a side note. Back to the camera settings. What we now have in this camera is a perspective lens, which is the same as a normal camera lens. And within this perspective lens, of course, you have the focal length, lower number, wider view angle, higher number, a shallower view angle, a smaller view angle. And as you can see, you can change the look of the image drastically when you're changing the focal length. You zoom in and out, but also the perspective changes. The monkeys, if you do a wide angle lens, the monkey in the back looks way smaller than the monkey in the front, but if you have a higher one, then the size of the monkey looks different because the perspective changes. And this way you can play around with how you want to view how you want to show your images, your visualizations. But this is just the perspective lens type. You also have a orthographic lens type, which means there is no lens in between. For this, I'm going to turn off the depth of field for now, which is in the camera settings, and then you have the depth of field and you turn it off. And with this, the light rays don't go through a lens, so you don't have this perspective change. So here, all the monkeys, they look the same size because the light rays just shoot straight out of the viewport, straight into the scene without any angle. This is useful when you want to have a perfect when you want to show perfect dimensions of, for example, a building or something. But otherwise, you don't usually use the orthographic view. And then you also have the panoramic view, which has a equi-rectangular panorama type, which is a 360 video rendering. But we're not going to go into depth into this because it's very complicated to, in the first place, to set up your scene, because you have to think about a 360 scene of your data. But also you don't see it in the viewport, you only see it in your final render. So every time you make a change, you need to render the image and see how it looks. It's very cumbersome. And then also when you render the image, it is projected on a 2D video, and then you still have to view it in a 360 video program. So we're not going to go into depth into this. So if we change back the camera to perspective, we get the, if we go back to solid to make it a little bit less crowdy, we have the perspective again, and the light rays are shut out in an angle from the camera view. And in this way you can also easily see it when you change the focal length, what's in the scene and what's not. I'm going to put it back on 50. And then of course, you already saw it, the depth of field. You only see the depth of field within the camera, of course. You don't see it in the viewport, so you need to be within your camera. If you go back into the camera view with 0 on your numpad or via the view option, you see the focal point of the depth of field in this case is an object, which is an empty object, meaning it doesn't get rendered in the final render, but you can only see it in the viewport. And this empty object is directly placed in between the eyes of the first monkey. But the thing is, I conveniently animated this empty so it can easily be placed on a different location, for example in between the eyes of the second monkey. And as you can see, it changes the focal point and the focus of the image itself. If we go back to the middle part, if we put a frame 50, go back to the camera, select the camera, then we're back in the camera options, and then we have the settings of the depth of field. The one setting that determines how shallow the depth of field is or how wide the depth of field is the f-stop number. The lower the number, the more shallow the depth of field. As you can see, if you put it super low, you only have the eyes in focus and the rest of the monkey is even blurred out. You don't even see, almost don't see the back monkey anymore. And if you put a higher f-stop number, all the monkeys are in focus. And that's it about depth of field. And then finally, the camera itself also has some artistic guides or compositional guides. If you want to have if you want to follow the rules of composition to make an image more attractive, you can go to the camera settings, go to viewport display, and then composition guides, and then you have a set of composition guides. For example, thirds. I placed the eye of the first monkey on almost a third of the image. Actually, I placed it on a third, but with a different focal length. So if you put the focal length higher again, as lower again, it will be on a third again, as you can see. And these compositional guides, they won't be in the final render, but only in the viewport, so you can use them to place your objects on thirds in the image. So that was it about the cameras within Blender, and we can now continue into the next section of this hands-on, which is gonna be the lighting. If you go to open, don't save, and then go to the second section, the second directory of the lighting, rendering and material walkthrough, and then open the lighting file. They agreed it with a piggy bank on a table. And if we now go into rendered shading, we don't see anything because there is no light. There is no light information, there are no light sources, so the light rays don't know where to get their information from. So the first major light source that we were talking about in the slides is the world lighting. Conveniently enough, it is already open, but in your properties panel, if you go to the world properties, there you have world properties, and if you select the surface, which is the surface of the world around your scene, they can change the material that is on the surface, and that will emit light. So if we then increase the white color of the scene, we see it gets evenly lit around the 3D scene with white light. We can also change this color to green, then we have green light, or blue, or red, But if you go back to white, then you can see it does light the scene, but it crushes down all the details on the object itself because it is a very diffuse light, uniform light. It also doesn't look real. There is no light that is so evenly distributed around the scene. So this is then the ambient light, the RGB light around the scene. But you can also use an image to light up your scene. And usually if you want realistic lighting within your scene, you want to use an HDRI image. But conveniently enough, I already added some presets in there with HDRI images in there. Now we have the world property preset world lighting on, which has just a normal standard world lighting. And if you click the little globe, you get some other presets: world lighting, RGB world lighting, no world lighting, and environment world lighting. The thing is, I added these presets, so by default it's not in Blender, but I'll show you how to add the HDRI later yourself. So if we select the environment world lighting, as you can see, it has now already almost a perfect lighting. And this is because an HDRI image has multiple light stops inside an image. So it has very accurate lighting in there. And I believe this one has 23 light stops. I'm not 100% sure. But if we look around now by using the middle mouse button, you can see the scene I have is lit with this living room HDRI image. And this way you have a very easy way of lighting, to have a really realistic way of lighting your scene. But the thing is, you are stuck with the lighting of the room. You have to find a proper HDRI image that fits to your scene. So it takes some searching, but there are some convenient websites that do have a lot of HDRI images, such as hdriheaven.com. I will write it in the walkthrough. But if we now go back to the camera view, you see nice lit, and this is just one HDRI image, nothing else. If we now go back to no world lighting, we're going to show you the lighting objects within Blender instead of the world lighting. So no world lighting preset. If we now go to collection 2, you see it is lit from above and nothing else. And if you look around the object, you see it has one single light source from above. If you look in the outliner, we see there is one sun that is pointing down on the piggy. So what you see with this sunlight is that it's very artificial. It's one direction, one light source, one color, and it's very uniform. But you do see with some directions, you see a lot of detail, because you can directly determine where the light is coming from and also determine how the shadows will fall on the object. For example, here you see perfect striations of the extraction algorithm, because this piggy bank is from an MRI scan and the isosurface is extracted in ParaView. And here you can see the resolution of the volume in the rings. But yeah, this is the sunlight, all the light coming from one direction. But if we go to the light options and then go to the properties panel and then go to the little light bulb, you see now we have a sunlight selected, but you also have a point light, which is one point that shoots light into all directions. So you can also place some very dramatic lighting in front of the piggy. And then you can determine exactly where you want to put the light. Further away, you get a more uniform lighting. Closer, you get a more dramatic fall off of the light on the object itself. And then you also have a spotlight, which is same as a lamp. You can pointed in a certain direction, and the light rays only come out or get collected within this cone. And finally we have the area light, which is very useful because it mimics a lot of the lighting that is used in a photographic setting in a photo studio, like those diffuser boxes. Those are also basically big planes with light. And then you can also see what different sizes do with the object itself. If you grab it, rotate it a little bit, you see it now has soft shadows. But what happens when I change the size to a very tiny size? The shadows get harder and harder. Now they're pretty hard shadows. If I make it bigger, we get very soft shadows. So this way you can play with it. And if you have, for example, one light source with one where you want to show more detail with, for example, you want to show this part of the face, you want to see the shadow fall. If you turn down the power a bit, oh, not so much. And you want to have another light, for example, which is going to be a bigger light, but a little bit more diffuse. It's going to be the fill light, which fills up the shadows in the back, on the back, so it doesn't look that harsh. As you can see, it fills up the shadows a bit, takes away the contrast a bit. And that's it about all the light sources. I mean, you can also change the color of the light source. For example, one of them is going to be a little bit reddish, and the other one a little bit bluish. Then you can have nice contrasting colors as well. And that's it about the light objects, the color, the power, and the size, and the effects they have. But you can also combine those light sources together to get a proper lighting setting, theoretical lighting setting. If you go to collection number 3, you can see, and then go to the camera, the piggy bank is lit with a 3-point lighting. If you scroll down, this is collection 3. You have a key light, which is the main light which lights up the object and shows the detail on the object. And then you have the fill light, which is going to be the light from the other direction, which is going to fill up all the shadows itself. If you remove that, you can see shadows get more pronounced, but with this fill light you fill up the shadows so you can see a little bit of detail in there. And then finally you have the rim light, which is a light from the back which creates a separation between the dark background and the object itself. And as you can see, it's now a white rim light. If you turn it off, you see there is no separation between the background and the object itself. And you can also give it a funky color if you want. And that's it about the lighting of Blender, the basic light sources, the major light sources, the global lighting and the lighting objects and the different lighting objects. And now that we know where the light information is coming from, we need to know how it bounces throughout the scene. So for this, we're going to open up the materials file. We don't save, go back, go to the third section, which is materials. And when you open up the material file, you are greeted with 3 spheres. Material sphere 1, 2, and 3. And those we're gonna apply some materials on and see what Blender can do with materials. So for us to see the materials, we first need to change the shading to rendered. And for now, all spheres are the same. They are all a white ball. But we are gonna change that now. So if we select the first ball and zoom in a little bit, and then go to the properties panel, and then go to the little red ball, not the globe, the little red ball, which is gonna be the material properties, you can see it already has a basic material on there. This basic material is a diffuse BSDF, and as I told you before, Here, when the light ray has an incidence on the material, it bounces off in a random direction. And as you can see, within this material settings, you have different panels. The viewport panel, which is something we're going to skip because we just want to see the current material. The preview, then you can see it within a tiny little window instead of your viewport. I personally never use this preview window. And then we have the surface panel, which is going to be the material that is applied to the surface of the object, so what it looks on the outside. And then we have the volume panel, which is what it looks like on the inside. If you don't have an outside and you have a volume and you put a volume material on there, you will get a volume representation. But we're not going to go into this volume representation for now. That's going to be for the next advanced course. And the other settings we're not going to do anything with. So we're going to go deeper into the surface panel, because that is what makes a material look different in your scene. For now, it has 3 or 4 settings. Surface, which is the BSDF, the way the light rays are bounced off. Color, which can change the color, of course. You can change it to red, you can change it to blue, you can change it to green. And as you can see, this material is also added to the other balls, so the other balls also change with it. And then you also have roughness, but funnily enough, it doesn't do anything on a diffuse material, because a diffuse material already has a random bounce on the object. So roughness doesn't do anything, because what roughness does is create a rough surface. For example, when you have a glossy surface, and you have the roughness all the way up, it will become a diffuse surface. And the normal mapping, which we're not going to do anything with, because this is a basics course. This was the diffuse BSDF, but you have a whole selection of materials where some of them we're going to apply to the balls. Next to the diffuse, we also talked about the glossy BSDF. And this glossy BSDF makes the ball look reflective. As you can see the whole scene around it in the ball itself. It makes it look like a Christmas ball. And then you have the same settings, colors, but also how it reflects the light. Usually I keep it on the same thing, the GGX. But as I told you, if I put the roughness up, the ball gets a little bit rough, and the reflection is a little bit more random. But you can still see the scene. But if you pump it all the way up, it becomes a diffuse ball again. So then you can make a diffuse material with a glossy BSDF. So it depends. You can be very creative with these material reflection functions. And then we gonna go and apply the glass material. As you can see, it took over the roughness, so you cannot see anything with this glass material now, because it's a rough glass. But if you remove that, you have a transmission surface, so the light goes through it and reflects in it and outside it. As you can see, it has some characteristics of glass, and it has the refraction in there, and you can change that with the index of refraction, how the light interacts with the glass itself. I think it was on 1.4. I'm going to keep it that way. And then finally, of course, what we talked about is basically the only material I usually use when it comes to quick prototyping, because it just covers every single thing. But as you can see, it adds a lot of settings. And it might look daunting right now, but if you know the basic properties of this BSDF, you can go around and play with it more. As you can see, it has the base color. It's just a color change. It has subsurface scatter, which I was talking about. It makes the object more absorbing of light. If you put that down a little bit, you cannot really see it on the ball. It's very hard to see in a ball. You need to have a real object. And if we turn it off, again, and for example, as the name says, metallic, you can create a glossy surface, but it's not exactly the same as a glossy surface. It has some extra features in there that makes it a little bit more realistic looking. And if we then also change the roughness, you can see it looks like a perfectly rough metal ball. And then of course the same thing with the glass shader. You can also do this with the BSDF. If you put on the transmission, you don't see anything. That's because some settings conflict with each other, because a metal cannot be transmissive. So if you want to use the transmissive, you have to turn off the metal. As you can see, it becomes a glass ball. Turn down the roughness. It has the same thing as the glass ball as before, but also here you have a transmission roughness, which is not the same as the normal roughness, which is on the surface, but the transmission roughness is the roughness on the inside of the glass bowl. So if you turn it up, the glass bowl is still reflective, but the inside is absorbing light. It's kind of like a volume, but it's not. And then finally, we can also make a light out of this bowl if we give this material an emission color, for example, I don't know, red. Then we have glowing red balls. And then you made a light source out of your object with a material instead of a light object or a global illumination. And finally, behind the scenes, everything is controlled by a node-based interface, which we are gonna go into the advanced course and not in the basics course. Here is the shader editor. As you can see, it has a shader output, a material output, and here it has the BSDF with all the settings, but you can make a whole network and make a super creative material. Now that you've seen everything about how the light starts, how the light rays get the light information, and how the light rays bounce through the scene based on these materials, you also might have noticed some noise, for example here, some specks, and we are going to cover now some stuff through the slides which are going to reduce these artifacts and give a better quality render in the end, and also increase the performance of the renderings. So for this, we're going to go back to the slides. So quality and performance. Blender is really good at making realistic scenes, realistic lit scenes, but it also has some downside. It takes a lot of time to render these images without noise or without so-called fireflies. And the basic two artifacts you see in Blender are noise and fireflies. And the noise is kind of like a homogeneous distributed noise on the image, mostly in the dark areas, and that is easily removed with some nifty tricks. And then you also have fireflies, which are very bright specks, also mostly in dark areas. And the causes of these artifacts are, for noise, the randomness in light sampling per pixel. For example, if a light bounces through the scene, it picks a light source at every bounce at random to shoot a shadow ray to. And this randomness then also creates different light values to any adjacent pixels. So then you get a different intensity in pixels, but eventually when you shoot enough rays, they will merge into the same color. So the randomness in light sampling creates noise. The low amount of ray cost per pixel, as I said, the more rays you cast, the less noise you get. Lack of visible light sources for the camera. If the camera is enclosed into a confined scene and there's only, for example, one window in the scene where light is coming from, the light rays first bounce throughout the room 100 times and maybe terminate before they find the light source, and the other does find the light source, and then that way it's hard for the light rays to find the proper light source. So one trick you can do is add somewhere a light source extra so the noise will be reduced. The same thing, of course, then a busy scene in an enclosed geometry, which is the same thing I explained. It comes down to the same thing as not enough visible light sources. And then you have the causes for the fireflies, which is light paths of a low probability with a high intensity light. For example, if you have a specular area and you have a very tiny light, there is a very small chance for a light ray to exactly hit the highlight, the specular highlight on that object and bounce toward the light. And that probability is very low, but the intensity is very high. And then the next pixel that hits it next to it misses it. Actually, this first step, the light paths of a low probability with a high intensity light, is better explained with the previous image. As you can see, there are 3 rays shot adjacent to each other, and the green has a speck, and it's because it had a random chance of bouncing off this diffuse material exactly on the specular highlight of this material, and which has a very high intensity because it's directly from the light source itself. So this green light has a very high value, while the red lights, they are bouncing through the scene without touching these white in high intensity areas of this glossy surface. So they are of a lower light, and then you get this green one which is white, and the other 2 are black. So yeah, specular reflections and glossy and glass surfaces are exactly what causes these high intensity values. And then you have small intense light. If you increase the light size, then you also increase this white spot, so you increase the chance of rays hitting this white spot, and that way you get less specks. So solutions, yeah, well, basically I already explained some solutions, but increasing the amount of bounces, amount of samples or bounces through the scene will reduce the noise. Introducing more light sources or opening up your geometry a little bit so that light rays can escape. But also denoisers within Blender are actually pretty good for some scenes. If you have a lot of detail in your scene, they can sometimes be washed away if you use it too intensely. But the denoisers are pretty good in Blender. And then for fireflies, yeah, of course, reduce the glossiness. So then you spread out the white spot on the glossy material, the specular reflection, or increase the size of the lights. Then you also increase the white spot on the area. Then the probability of hitting this intense light area is easier. And then you have filter glossy, which diffuses out the glossy reflections. Actually, it shoots the ray and it looks glossy, but within the computation it diffuses the light. And finally, the magic setting is clamp indirect. These indirect values of high intensity values, if you decrease the highest intensity something can get, the closer to the other values it will be. So the less samples you need to get the average down to the other values. So clamping the indirect to a little bit higher indirect value of what the average value would be will drastically reduce the fireflies. And then finally, we have performance, which goes hand in hand with the quality. If you want better performance, you can reduce the resolution, but you get a lower resolution image, but it's rendered faster because it has to shoot rays from less pixels. The number of samples, but yeah, then you get less quality, but the performance is better, the render is faster. The number of light bounces, which can be finicky because some lower amount of light bounces can still look very real when you use that, because if you crank up the values of the light bounces, you get a very, very realistic looking image, but sometimes the realism between 3 bounces and 30 bounces is almost negligible. And of course you have the GPU versus CPU. If you have a proper GPU in your system, the rendering goes super fast and super smooth. But also the same goes to CPU, but the GPU is generally better at computing these renders than a CPU. And also some materials are very, very intense for computation. For example, subsurface scatter, then a light ray bounces within the material itself, and then it takes a lot of time to bounce out and to terminate this light ray to find the light source, for example. The same goes for a volume material. It bounces in the volume hundreds of times and then goes out, and then it takes a lot of time to compute. And of course, you can also choose for lower samples and then just apply a denoiser to remove the noise, and then the render is also faster. A little bit more about the denoise. So for example, if you would render a skull, in this case I rendered it in multiple settings. This one is with 16 samples per pixel. It takes 7 seconds to compute, which is relatively fast, but you do have a lot of noise in there. And the right one is 1024 samples, which takes 4 minutes and 25 seconds. But you don't have any noise. It's a very crisp image. Yeah, you do have a tiny little bit of noise in there, but it looks still super nice. But if we then introduce the denoise, for example, on the 16 samples, you do get you do remove the noise, but you do get some weird looking artifacts inside. If you look here, there's nothing there, but there you see some kind of blob where the black values are smooched together. Also, you lose some details. For example, the rings on the skull are gone, so everything smooths out a little bit. It washes it out. But there is you just have to find the, as we say in Dutch, the gulden middenweg. If we increase the samples and do a denoise, you do get some details back, and you remove also the blobs within the dark areas. So you come closer to the 1000 sample image, but it is 20 seconds of computation instead of 4 minutes and 25 seconds. So that's a huge performance boost. But yeah, there are still differences which the eye sometimes doesn't catch. But if you difference out those images, for example, the 16 samples denoised with the 1000 sample no denoise, you can see it still has some values that it missed, and some details could be missed as well. But yeah, the higher you get with the samples plus denoise, the least amount of details are lost. So for example, 64 samples denoised is already a good alternative for 1024 without denoise. So now that we went through the theoretical part of the quality and performance within Blender, we are gonna go into Blender now and see how it works with Blender itself. So when we open Blender, and then we open the last section of the rendering, lighting and material section of this course, we're going to open this quality and performance section, and then you see a scene with different objects and a simple camera and simple sun lighting. And if we put that to rendered, you can see it has some glossy surfaces, some diffuse surfaces, and as you can see, it already generates a lot of speckled light. So we are going to try and fix that. But first, we're going to look at the render settings. So within the properties panel, you have a render properties tab. And within this render properties tab, you have all the settings you need to render your final image, which could look a little bit daunting because it has a lot of settings, but you don't have to tweak them all to get the best results. First part is of course the render engine, cycle and Eevee. We are only using cycles, we don't use Eevee at the moment. Feature set we don't have to change, just to use the supported feature set, because you also have an experimental one and then you get some extra options. Device, GPU versus CPU. If you look at how fast this is rendered with the CPU, it's done right now. Compared to the GPU, it goes a bit faster with the GPU. So in my machine, the GPU is faster than the CPU, so it's better to use the GPU. And then we have the next section of importance, which is the samples. This is where you set how many samples are shot per array. So you have two settings. One is for render. It's actually when you start rendering your image, it will have a higher amount of samples than it has in your viewport, which I have right now. This is your viewport. So it shoots 12 rays per pixel, which is done right now. If we go back to the camera view, but if we then, for example, do 32, it will render for a little bit longer and tries to get a better accurate image. But in this case, it only generates more fireflies, which is not good. And the next section is the light paths, which is directly underneath the sampling. And here you set the amount of bounces in the scene. For now, it's maximum 12 bounces per light ray, and then it gets terminated. So if we set that to, for example, 4, it already reduces the render time instead of 12. And diffuse and glossy is how many diffuse reflections you have, and glossy, how many glossy bounces you have, how many transparency bounces you have. And usually just keep it at default. And sometimes reducing this diffuse and glossy to 3 or 2 already gives a nice looking image. I mean, do you see the difference? In this scene you might not, but in other scenes you do see the difference. So usually what people say is just keep it on a lower number, but a couple of bounces, like 4 bounces I usually do. So yeah, now that you put all the settings in there, what happens when you render the image? For this, when you want to render the image, you go to the top and you press render image, and then it will render out the image. And as you can see, it will do it block by block, and each block is either a CPU core or a GPU core, and this way it renders out the image perfectly. But still, fireflies. If you hold your right mouse button, you can see that these are dark values. If you look at the bottom of the screen there, and as you can see, the light areas are very, very high values. They are, for example, RGB on this is 310.5, but one above is 0.02, 0.01, 0.01. Which means there's a huge difference between those values, and that's why trying to reduce these kind of things that generate these fireflies is a good idea. And then finally, if you want to save this rendered image, you can go to image and then save, and then you save it into a render file, rendered, and then you can save this image in whatever directory you want. So yeah, now that we've seen how you can render this image, we want to also see how we can reduce these fireflies, for example, or the noise within the shadows. First off, we're gonna clean this image. We're gonna remove the fireflies. Well, if we saw in the slides, we saw some ways to reduce the fireflies. And those were reduce the glossiness of the surfaces. So if we go and select this surface, and then go to material, and then give it just a little bit of roughness, as you can see, it washes out the white spots. And as you can see, it does still create fireflies, but they are more distributed, and they will eventually spread out over the whole reflective dark area here, so it looks better. But also this is also still rough, and this one is still rough, And as you can see, it still generates some fireflies, but it already reduced it. And if you want to completely remove it, of course, we can also completely make these things diffuse. And of course, then you don't have fireflies, but this doesn't work if you want to have glossy surfaces. So if we go back to our previous scene, we have still the fireflies. So we saw that we can reduce the fireflies with reducing the glossiness, because it increases the probability of these lights hitting this super bright areas. So another way is to increase in this case, the sun, the size of the sun, or the angular diameter of the sun. So if we increase that, you see that the reflection becomes higher, but it will reduce the number of fireflies, because there's a high chance of all the light rays hitting these light areas and distributing better over the scene itself. But yeah, now you have soft shadows and you have an unrealistic sun. So if we reduce that again, go back to the normal sun, we're gonna go to the render settings, and within this render settings you also have some extra settings which reduce the fireflies as well. Then you have the filter glossy, which will deblur the sharp light sources without showing it. As you can see, it removes the fireflies, but the thing is, the reflections are now not realistic. So yeah, it's, do you want fireflies, do you want realistic or not? So if we put that back to 0, we get the fireflies again. And finally, we have the magic setting, which is clamping indirect. If we set that, we just saw that the average value was 0.01, for example. So if we set this to 0.5, you do see that in the beginning, it will generate these slightly lesser intense fireflies, but they will diverge eventually into the same values as the adjacent pixels. Well, that was it about the fireflies, but what about the noise? If we go to collection 2, you see a box, and this box only has a light source outside and not inside, and it only has one window, and you already see it from the outside. There's a lot of noise going on inside. So if we now select Suzanne in a box in the outliner and then press the point or the dot on your numpad, or press the tilde on your keyboard and then go to view selected, then you go inside the box. Now we're inside the box with Suzanne, and as you can see, there's a lot of noise going on because that is the only light source that is available, and all the light rays around it, they will bounce throughout the scene and do not find the light source itself. So as we explained, we can either open up the window to reduce the noise, or we can add other lights inside, add another point light. But yeah, that's kind of pointless because then you don't have the nice sun ray going inside. But you can reduce, for example, the light, and then you still have it, but then the noise will be less because there's more light information inside. That is one way, but if you remove it again, another way is, for example, to just wait hours and hours for, I don't know, thousands and thousands of samples to be created of the light for each single pixel, and then eventually you'll get a smooth dark area. Also, we can just use the denoise. If you go to the render properties and then look underneath sampling, then we have a denoise section. And if you activate it for your viewport and then select open image denoise, it has to load some kernels to use this denoise, which can take a little while to calculate. So I'm going to pause it for now and continue when it's loaded. So now that it loaded the kernels, you can see the dark areas are smoothed out and the noise is removed. But the thing is, it also creates some artificial looking blotches, and if you move around, it looks like everything is painted in. It is an artistic choice. Maybe you like it, maybe you don't. But if you wait long enough, it will also generate a good image. And it will do it faster than the normal rendering would do it. So yeah, that was it about the quality and performance of Blender. I think now you are prepared enough theoretically to do the assignments yourself. So I would just say dig in, and if there are any questions, contact us on Discord.